Welcome to Study Loop.
The total of the moment of inertia for a typical dancer is equal to 7% times the moment of inertia of the head plus 13% of the moment of inertia of the arms, and then plus the 80% of the moment of inertia of the trunk and legs of the dancers. So we know when the head starts spinning, it's kind of like the sphere spinning. Okay, so that's why I head here can be equal to I sphere, which is equal to 2/5 mr squared. And then when the R start rotating, it will rotate like a rod, rotate through one end of the rod. Okay, so I have I on here is equal to I rod, which is equal to 1/3 ml squared. And when the trunk and the legs start rotating, it's rotating like the rectangular plates, which is rotating about the center of the rectangular plates. And that's why we have I trunk and legs here is equal to I rack, which is equal to 1/12 m times a squared plus b squared. So now we can do some rearrangement here for the equation. So eventually we'll have the total moment of inertia is equal to capital M times 0.028 r squared plus 0.043 l squared, and then plus 0.067 times a squared plus b squared. We know capital M here is the mass for a typical dancer, which is about 65 kilograms. And R here is the radius of a human head, which is about 0.1 meter. And L here is the length of the arms. And the length of the arms for a female dancer is about 0.80 meter. A here is the distance between the chest and the back, which is about 0.25 meter. And B here is the width of the shoulder, and this is about 0.4 meter. If we plug in back to the equation, we'll have I is equal to 65 kilograms times 0.028 times 0.1 meter to the power 2, and then plus 0.043 times 0.80 meter to the power 2, and then plus 0.067 times 0.25 meter to the power 2 plus 0.40 meter to the power 2. And this will give us the total moment of inertia of the body should be equal to 2.78 kilogram times meter square. So now let's determine the rotational kinetic energy, which is equal to 1/2 I omega square. So we know the moment of inertia is equal to 2.78 kilogram times meter square. And the angular velocity is given as 72 revolution per minute. If we convert it to radian per second, it's about 7.54 radian per second. So now let's plug in back to the equation to determine the rotational kinetic energy, which is equal to 1/2 times 2.78 kilogram meter square, and then times 7.54 radian per second to the power 2. And this will give us the rotational kinetic energy is about 79.0 Joule. And these are the answers for this question.